So this week we are going to wrap up our online version of the course by talking about slope-intercept form. Now this is something that would usually be built into all the labs that we do, but because we had limited opportunities to do labs in this type of a lab experience, we do need to talk about this because a lot of you are heading into 30 next year, and this is a relatively important idea that will allow us to be successful at the next level. Now you're probably familiar with the slope-intercept form from math, right? Y equals mx plus b, where y is the responding variable, it's the thing we're measuring. X is the manipulated variable, the thing we're changing. It's always going to be that way. We're always going to have y on our responding variable on the y-axis, our manipulated variable on the x-axis. And then the slope of the line, so once we get that line, m is the slope, and then b is the y-intercept. In this case, it's 0, but b is the y-intercept. So that's the parts of slope-intercept form. Now we can calculate slope, and you guys have done this before, but it's just rise over run, y2 minus y1 over x2 minus x1. You pick 2 points on that line. You take their x and y coordinates, find the slope. That's the slope of that line, that's m. Now when we do experiments, we're trying to find out something about the universe in physics. And so slope-intercept form helps reveal us some of these things about the universe. We change something, that's our manipulated variable, and we measure something. And based off of those values, we can find something else. That's where the slope is important. The thing that we're changing and the thing that we're measuring, maybe we find out how they're related, but it's that slope that is almost more important because it tells us something when we look at some of these equations. Now, when we look at y and x, we do have some different relationships. If we have, like in the previous example, y varies directly with x, we have a direct relationship. It's a straight line. We can have different relationships though. Like for example, if y varies directly with x squared, we get this parabolic, this exponential relationship. If y varies directly with x to the 1/2, or if there's y varies directly with root x, the same thing, we get this parabolic relationship. And if we have an inverse relationship, that graph is going to go down. And we can even have an inverse squared relationship. This probably looks familiar to when you're talking about, when we were talking about gravity. Big G, m1, m2 over r squared. That's an inverse squared relationship. It looks like that. Now, the first one's straight, so that's great. Like if we think of y equals mx, it's a straight line. The slope of the line is m. With the other three, though, we do need to manipulate these graphs in order to get a straight line so we can find the slope. And the way that we straighten the line is we're always going to be talking with the manipulated variable. We're going to be dealing with the manipulated variable, and the relationship tells us what to do. If I have a parabolic relationship and I want a straight line, I have y here. Well, what I would plot is I would plot my x value squared. If I did that, I would get a straight line. If I had a parabolic relationship and I wanted a straight line again, I would plot root x on my x-axis and I would get a straight line. And then finally, for this inverse relationship, it really does depend on the relationship. If it's just a 1 over x relationship, I plot that, I get a straight line. If it's an inverse square relationship, I need to go 1 over x squared, and then I get a straight line. Now, these straight line graphs are great because then again, we can find the slope, and based off of that number for the slope, we can find out something algebraically. So here's some examples. In order to do this, first we need to put these into slope-intercept form. So we need to get whatever our responding variable, we need to get that by itself, that's our y. We need to get our manipulated variable by itself, that's our x. Something might be multiplied by the manipulated variable, that's our m, and maybe we have a y-intercept, that's our b. So we need to rearrange this equation into this form. So VI is my responding variable. Let's rearrange this equation to get VI by itself. So I'm going to subtract AT from both sides because I'm adding AT. So I get VF minus AT is equal to VI. Let's put it into this form exactly so we can form a habit and it gets easier to see the parts. So I get VI equals, then we have something multiplied by our manipulated variable. Our manipulated variable is T. So I have my minus AT and then plus VF. If we think about this then, here's my Y. Here is my x, my t. My slope is my minus a. And then I have a y-intercept. That's my VF. So I'm going to have some y-intercept on here. My final velocity, whatever that is. Then I'll have this line here, the slope of which is minus a. So when I look at this now, the slope of this line is going to be minus my acceleration times my time plus VF. So we're going to have this type of graph and these parts on it. Here's another one. So A is a function of M. So let's again get A by itself. So A would be equal to F over M. Now in order to again see these relationships, it's nice to take that manipulated variable out. So another way to write this, and this is going to feel weird at the start, is F times 1 over M. Right? That's the same as this. I haven't done anything differently. Now this is good because this shows us the relationship if A is graphed and M is graphed. That's an inverse relationship. So if I were to plot A as a function of M, I'm going to have an inverse relationship. If I wanted to have a straight line, this equation tells me what to do. I need to plot A here, that's my responding variable. I need to plot 1 over M as my manipulated variable. Then I would have a straight line. And the slope of this line would be equal to F, the force. Right? We have y equals mx. Here's my y. This is what's plotted on my x. What remains is my slope. And in this case, it's F. So my slope here would be F when I get this straight line graph. So when we have inverse relationships, we do need to plot something different in order to get the slope line. Here's another one. Let's say we plot t as a function of L. So maybe we rearrange this equation a bit. I can also write it this way, 2 pi over root g times root L. This tells me that t and L have a parabolic relationship, right? If I were to plot t as a function of L, because it's root L, it's going to look like that. Now, if I wanted a straight line, my equation, so here's my y, and here's my x. Again, we want to get x by itself because we can see what we have to do with it, and also we can see the slope a little bit better. So I need to plot root L, and then I would get a straight line. The slope is the rest of this. And so now here it's a whole term. So my slope is now 2 pi over root g. That is my slope algebraically. And if we think about this, like maybe we're on the moon. We have different pendulums at different lengths and we take their period. We know what pi is. That's 3.14. 2 is just a number. But if we find the slope of this graph, now we can find out what g is on the moon because we have a number. We have 2 other numbers here. Then we can solve for that other variable. And that's kind of the power of these relationships. We don't need to do just one trial. We have multiple trials, and we can get it figured out. One more. Now we have ek as a function of v, and that's v squared. So if we were to just plot ek as a function of v, we see that it's v squared, so we would have an exponential relationship. If I wanted a straight line, I would need to plot v squared. So I would take my v values, I would square them, and then I would have a straight line. So my responding variable is ek. My manipulated variable is v. What's left is my slope. And in this case, it's 1/2 m. So my slope is going to be 1/2 of the mass. So that's how we use these relationships to straighten the line, and then more importantly, how we determine the algebraic significance of the slope. Because that will allow us to unlock some of these other variables. Once we draw this graph, I've spent my whole experiment concerned about v and ek, because that's what I'm changing, that's what I'm measuring. As soon as I draw this graph, I can forget about those. Now I only am dealing with the slope. I know what the slope is as a number, rise over run, and now I can find out, because I know what the slope is as an equation, I can find out what the other variable is. So let's look at this question. So here we have some natural and artificial satellites of the Earth. So we have the ISS, Hubble Space Telescope, a GPS satellite, and the moon. So these are things that go around the Earth. And we are manipulating their orbital radius, and we are measuring their gravitational field strength. So if you think about last week, remember gravitational field strength is big G m over r squared. We are going to use this data to try to find a value for the mass of the Earth. And this is something similar to what astronomers did to find the mass of the Earth, is they looked at how things orbited the Earth and the force of gravity acting on those things, and then they were able to find the mass of the Earth causing that gravitational attraction. So we're going to take this data and we are going to put it into a graph. Now you can see here I'm using my calculator. You are probably going to draw it by hand, but when I graph this stuff, you'll see I have an inverse relationship. And looking at the equation, it's an inverse square relationship. So what I need to do to get a straight line is I need to take my x values, which is what I'm doing here, and I need to plot 1 over x squared. Or in this case, it's 1 over my second list squared. I'm going to plot that. So now I've manipulated all that data. I'm going to go back to the graphs that I drew, and I'm going to change my x list to L3, because that's where this new manipulated data is. In this week's assignment, you'll just be drawing this by hand. But in the future, using your calculator is a great way to manipulate it quickly. But when I go to the graph now, and I change my window, you'll see that now I have a straight line, which is great. So this straight line, it gives me my value for my slope. So I can take this straight line now, and using my calculator, I am going to find the line of best fit. And from that line of best fit, I'm going to find my slope. So my slope is 3.98 times 10 to the 14. So that's my slope numerically. So 3.98 times 10 to the 14 is my slope numerically. If we think about what we plotted, so again, I have my gravitational field strength as my function of r. We had an inverse relationship. And then to get a straight line, so we could have rearranged this equation beforehand and saw what we had to do, right? I could also change this equation to gravitational field strength as g times m times 1 over r squared. That's the same thing. What this equation tells me is if I want a straight line, I need to plot 1 over r squared on the x-axis. And when we did that, we got a straight line. Now, if we think about these parts, so here's my responding variable. Here's my manipulated variable. What's left, so if we think of y equals mx, what's left is my slope. So my slope is equal to big G times m. Now think about your slope numerically. So our slope numerically again was 3.98 times 10 to the 14. Algebraically, this slope was big G times m. And that's kind of the point. That is the whole point of these graphs in physics, is taking this data that we've measured. So we've manipulated something, we've measured something, plotting it, getting a line of best fit, and then using the slope of that line of best fit. We now have this number which takes into account all of these trials and also the space between them. So I have my value for the slope, a numerical value, and I also have an algebraic value, an algebraic equation for the slope. You'll notice that in this now, I don't have r and I don't have g, because that was my responding manipulated variable in my graph that allowed me to find that slope. Now I can find out what the mass of the Earth is. So I take my 3.98 times 10 to the 14, divide by big G. So 3.98 times 10 to the 14 divided by 6.67 times 10 to the negative 11. And I get 5.97 times 10 to the 24 kilograms. So I look at things that are orbiting the Earth, and from this line of best fit, I can determine the mass of the Earth. Now you might ask, why don't I just use one point and plug it into an equation? And students do that a lot in physics, and they get the question wrong. The reason why is, if we think about all of these things, that like this might not be a perfect value. If we think about something orbiting the Earth, so if we think about something as an option to use the slope, we want to. As soon as we draw that line of best fit and have the slope, we forget about all these values. We forget about the g, we forget about the 1 over r squared, and then we just focus on what is the slope and what does that slope tell me. Orbits the Earth. Maybe it's not an exactly circular orbit, right? Maybe it is a perfect circular orbit. Maybe just because of how I'm measuring, one of my measurements is a little bit off. The nice thing about doing our line of best fit, I guess that's 1 over r squared. So when we do this line of best fit and we have these different points, when we draw the line of best fit, it doesn't necessarily have to hit any of these points. But if I am just using this data, I'm picking that point and just solving it like an equation, that might be off by quite a bit. The line of best fit helps to mitigate some of those differences in measurement and just circumstances, and allows us to get a better, more accurate answer. So that's why when we have